had left yesterday. So today we'll try to cover 5G new radio numerologies, subcarrier spacing, resource block. These concepts we'll try to cover. And next part of my presentation would be on 5G new radio frame structure. So there are two parts. Let me try to cover both the part today. So first of all, let us understand the concept of numerology in 5G new radio. So yesterday we had discussed that in case of a 5G also, similar to 4G, we use orthogonal frequency division multiplexing, that kind of waveform. But the difference from 4G is that in 4G, we use a subcarrier spacing of only 15 kilohertz. We only use 15 kilohertz subcarrier spacing in case of 4G. But in case of 5G, for LTE, we use only 15 kilohertz. But in case of 5G, it is kind of a variable. We can decide depending upon the requirement or use case that what kind of subcarrier spacing we'll be using. It is not fixed like LTE. So in 5G, the subcarrier spacing which we use is 15 kilohertz, 30 kilohertz, 60, 120, and then 240 kilohertz. So 1, 2, 3, 4, 5. 5 different subcarrier spacing we use depending upon what band of frequency we are using, what is our use case. We will discuss about that. Now, what is numerology? So numerology is nothing but what kind of subcarrier you are using. So it is 2 to the power mu into 15 kilohertz. And here mu is nothing but your numerology, right? So when we say numerology is 0, that means my subcarrier spacing is 15 kilohertz because 2 to the power 0 into 15 will be 15. So can you tell me that in case numerology is 1, what will be my subcarrier spacing?
30 kilohertz.
Yes, so that will be 30 kilohertz and so on. For numerology 2,
60.
And for 3,
120.
yes, and for 4,
240, sir.
240.
So basically numerology is nothing but what subcarrier you are using. Mu0, mu1 up to mu4, mu0 to mu4. Mu is your numerology. So 15 kilohertz, 30 kilohertz, 60 kilohertz, 120 kilohertz and 240 kilohertz. It's very simple to understand about the numerology. But if you read the specification document, it takes a long time to understand this. Okay, now what is resource block? Many of you might have worked in 4G. Can you tell me that in case of 4G, what is the concept of resource block? Anyone? Any of you can tell me concept of resource block in 4G? Okay, no problem. Let us discuss about 5G straight away. So in case of 5G, 12 resource block, 12 subcarriers, but they have to be consecutive, continuous. 12 continuous or consecutive subcarriers, we call it resource block. The definition of resource block is slightly different in 4G. There, not only subcarrier, but time is also defined. But in case of 5G, the resource block is only in terms of frequency domain, that is 12 subcarriers, that is contiguous. So 1 RB is equal to 12 subcarriers. So just see that in case we talk about numerology 0. So in case of numerology 0, my subcarrier spacing is 15 kilohertz. So one RB will have such 12 subcarriers of 15 kilohertz. So what will be bandwidth of one RB in case of numerology 0?
180.
Right.
180 kilohertz, sir.
So it is 180 kilohertz. You can see here. Now can you calculate it for numerology 1?
360.
Yes, 360s, because here 12 into 30
30.
kilohertz. So that is 360. Very right. And for numerology 2?
720, sir.
So 720, and then numerology 3 and 4 you can calculate, just double it, 1440 kilohertz and 2880 kilohertz. I hope this concept is clear to all of you, that the bandwidth of RB is doubling when we are moving from one numerology to next numerologies. I hope this concept is clear. Now the same question which I had discussed earlier, slight difference is that here let us take a channel bandwidth of 100 megahertz, and here let us take subcarrier spacing of 60 kilohertz, and guard band will be here 1370 kilohertz both side. That means in case I have this 100 megahertz, then I have to leave 1370 here and also 1370 kilohertz here. Whatever is remaining is called transmission bandwidth. So please calculate the transmission bandwidth. Please calculate the transmission bandwidth and tell me. Yeah, so Kiran
97. This one, sir.
97.26, sir.
97.6.
26 megas.
So, okay, 97.26 megahertz is your transmission bandwidth. Now, can you calculate number of subcarriers? You have to divide it by 60 because subcarrier spacing given here is 60.
1621.
1621.
So number of subcarrier is 1621.
21.
So everyone has understood? Anybody is having any question? No doubt? So number of RB now, can you calculate? Can you calculate number of RB? 135 Steve Krishna ji has told. Anybody else? What's your calculation?
Yes, sir. 135.
Yes, you all are right. 97.26 is your transmission bandwidth. 1621 is your subcarriers and 135 RB. So that means in case you have 100 megahertz and you have subcarrier spacing of 60 kilohertz, you will have 135 number of resource blocks. RB is resource block. Very nice. So this we have already covered, that what will be bandwidth. So I'll just skip. Right. So can you do one more calculation? I think this we had done yesterday. So here also I'll just skip. Now I'll tell you the relation between these numerology, frequency band, cell size, etc. Just see here. Before that, let us understand UV channel bandwidth. So what is an UV channel bandwidth? So basically, when I was saying 100 megahertz, so I was talking about this one. The complete, if suppose a particular, in a particular band, certain chunk of spectrum is given to me as an operator by say DOT. So that is my channel bandwidth. So in our example, it was 100 megahertz, right? Now I have to actually leave guard band both side. So this side also I have to leave certain guard band, and this side also I have to leave certain guard band, right? And these two guard band can be different or symmetric. It is possible in 5G. We'll discuss that it is not necessary that guard band both side has to be same. It depends upon the numerology, right? So you may use multiple numerology within the same channel bandwidth. You can divide into parts and use different numerology. So we'll have different guard band for different numerology. We have different guard band. I'll show you the figure later on in this slide. Now, once you have removed this guard band, whatever is left is called transmission bandwidth. And this transmission bandwidth will have n number of resource block depending upon how much bandwidth you have. Now, when you actually transmit or receive, not all RBs are used, right? Not all RBs are used. So whatever number of RBs are active, they are called active resource block or transmission bandwidth in terms of RBs at that point of time. So I hope you have understood, and this picture is directly taken from 3GPP specification document. This one you can download and see. Okay. Let's go to next slide. Here what I was telling that, first of all, let me explain this. So what I'm trying to say, suppose I have this much channel bandwidth from here to here, and suppose I use one numerology here. So corresponding to that numerology and band, this is the guard band. On the other part of the channel bandwidth, say I am using numerology Y, which is different than X, and here also the guard band is defined is different. So it is looking slightly bigger in this picture. So it is possible to have asymmetric guard band depending upon the numerology for the same bandwidth. Similarly, the location of those subcarriers or PRBs are fixed in the standard. What I mean is that you cannot just start your subcarrier from any point. So those points are already defined, right? So in case suppose channel bandwidth is given to you by DOT, and DOT will just give you that. So you have to look at the specification and see that first of all you have to leave guard band. So your RB may not start straight away here. Your RB may start or subcarrier may start here, right? So it is possible that even after leaving guard band, you have to leave some more space just to align with the subcarriers or RBs as defined in the standard. So I hope this is clear to all of you. Someone was saying slide is not changing. I think you should reconnect in case your slides are not changing. It is normally bandwidth issue towards the receive side. So you can connect and disconnect again. Okay, I was telling about how this guard band or transmission bandwidth configurations are there. This again is taken from the specification directly. So one is that we calculated, same thing will be in a table in the specification. So our example, if you look at our example was we had taken 100 megahertz channel bandwidth. We had taken 60 kilohertz subcarrier spacing, and for 60 kilohertz subcarrier spacing and 100 megahertz, this we had taken the guard band from this table 1370 from both sides. If you subtract, you'll get transmission bandwidth. If you divide by 60, you'll get number of subcarriers, which is given here in the table 135. So either you can calculate or you can just straight away take it from the table given in the specification. So let us take one more example. Let's see that I have 50 megahertz bandwidth, channel bandwidth. I'm using say 15 kilohertz subcarrier spacing. So I will have about 270 RBs. Number of RB I'll get is 270. 0. Okay, so either you calculate or you can use the table. So now my question is, just see this table and try to find out some of the key aspect. Can somebody just look at the table and tell me the key aspect of it? So this table is for frequency range 1. Just look at subcarrier 15 kilohertz, that is numerology 0. You just see that after this point, they have given not applicable. So that means after 50 megahertz, they have given not applicable. What does this mean? इसका meaning क्या है? Anyone from you? Anyone from you? Just guess. Say yes or no in the chat box so that I know that you are able to understand.
My guess is that with this 15 kilohertz spacing, with the 60 megahertz bandwidth, you can't have 15 kilohertz of spacing.
Yes.
If it is 80 megahertz or 90 megahertz
Very
bandwidth.
right, sir. So the summary is that for numerology 0, the maximum channel bandwidth permitted is 50 megahertz. Similarly, for 30 kilohertz, it goes up to 100 megahertz. If you have 30 kilohertz subcarrier spacing, you can go up to 100 megahertz. In FR1, 100 megahertz is the maximum. And for 60 also, you can go up to 100 megahertz. So that is the summary, 100 megahertz. So this table was for FR1, which gives your number of PRB for a given configuration and also the guard band. Now let's look at this table. This table is for FR2, frequency range 2. When I say frequency range 2, it was 24 gigahertz to 52 gigahertz, if you recall yesterday discussion. So here also just see for 60 kilohertz, just see the 60 kilohertz is common in FR1 and also FR2. That is one of the key observation, that the 60 kilohertz was also there in FR1 and also available in the FR2. For 60 kilohertz, so 50, 100 and 200 up to this. So that means if you have 60 kilohertz subcarrier spacing, that is numerology 2, in that case, you are able to go up to 200 megahertz. And for 120 kilohertz, you are able to go up to 400 megahertz. For mu is equal to 3, you are able to go up to 400 megahertz. So just see, yesterday we had seen the channel bandwidth, which said that FR1 we have maximum channel bandwidth of 100 megahertz and FR2 we have channel bandwidth maximum of 400 megahertz. But there is a finer detail that in case in FR1 if you use only numerology 0, you can go up to only 50 megahertz. In case of numerology 1 and 2, you can go up to 100 megahertz. In FR2, if you use 60 kilohertz, then you can go maximum 200 megahertz channel bandwidth. Only when you use 120 kilohertz, you are able to reach to 400 megahertz. My question is that why I'm not talking about 240 kilohertz subcarrier spacing here? Mu is equal to 4. This table do not have. Any reason for it? Any guess from any of you? Please be participative. If any of you do not know, just speak something. Or just say do not know. Any guess?
No, sir. No.
Okay.
This 2 kilohertz,
Yeah.
that is not visible in the table, upper table, of course.
Correct.
What I said for the minimum guard band requirement for the 240 kilohertz is quite different. It is given in the lowest table. So that minimum
Yeah.
guard band for 400 megahertz, it is around 15,560.
Yeah.
So
So
that it may have to do something with that.
yeah. So till release 15 and 16, in a standard, they have said that for user data, numerology up to 120 kilohertz, numerology up to 3 will only be used. Numerology 4 will be used only for the signaling. That signaling, we call it synchronization signal block and physical broadcast channel. So that will only be used in the control signaling, not for the user data, and that's why they have not included in this table. They have defined guard band, but they have not included in the table because this table is primarily for user data. Okay, let me move forward. So let me stop here and take any question which you may have so that I answer and then proceed. Please open your
Sir,
mic and ask your question
sir,
related
sir,
to. Yeah.
sir, could you please sum up the last 4-5 slides, sir, once again, just briefly?
Last 4-5 slides. Okay. So, okay, let me sum up that in case of 5G, we have numerologies called numerology 0, 1, 2, 3, 4. When I say numerology 0, 1, 2, 3, 4, actually I mean the subcarrier spacing. So here I have 15 kilohertz, then I have 30, 60, 120 and 240 kilohertz subcarrier spacing. So that is the concept of numerology. Then I told you that for every numerology, how much channel bandwidth you can use. So for example, if I use mu0, the maximum channel bandwidth which I can use is 50 megahertz. If I use 30 kilohertz, then I can go to 100 megahertz. If I use mu2, I can go up to again 100 megahertz. This is in FR1. In FR2, so I'll be using mu is equal to 2. So I said that mu2 is both side in FR1 also and FR2 also, right? So in case of mu2, I can go up to 200 megahertz. In case of mu3, I can go up to 400 megahertz. And in case of mu4, it is only used for signaling. So this is not defined. And then for each numerology, you have a different guard band. Guard bands are defined. Is it okay to you?
Yes, sir. A small doubt is, sir, how the guard band has a physical significance of avoiding the interference. How this is different, sir? Here, some bands are dynamically these bands are different.
If you go higher in numerology, so your bandwidth increases. Subcarrier bandwidth is increasing. So because of that, your guard band requirement is also increasing, right? And that is defined in the specification itself.
Okay. Okay.
Right.
Right, sir. Thank you, sir. Thank you.
So
why,
let me.
why we are having a concept of numerology in the 5G? What is the practical aspect of having the numerology?
So very good question that why we are having concept of numerology, as 5G has various use cases. In one use case, we call it large coverage area or coverage for IoT coverage for rural areas, right? So there your latency requirement is less, data requirement is less, but coverage requirement is more, right? So there, if you use higher numerology, you may not be able to reach to that space. You have to use a lower numerology, and also the time guard band, which we call it cyclic prefix, is also higher, so that the inter-symbol interference can be avoided. The other example would be that if you need a higher bandwidth, you require to use higher numerology so that you are able to pack more data within, say, same time period, but you have 30 kilohertz or 60 kilohertz subcarrier. So within the same symbol time, you'll be able to pack more data. If you need higher speed, you need higher numerology, so that in a smaller time, you're able to pack more and more data. That's why this variable numerology concept is there in 5G, so that it is able to support various use cases. We'll discuss this in upcoming slides in detail.
So does it mean, sir, that in the 800, 900 band, we will be using the lower numerology, and when we go into the MM wave band, we will be using the higher numerology?
Very right, very right, very right. And that was true when I discussed, no, when you have more channel bandwidth, you are using higher numerology, and more channel bandwidth will be available only in higher bandwidth side, higher channel bandwidth, higher bands, right?
And sir, what is the concept of resource block? Why we are using it? Just save the transmission power or anything else?
No, no, no. It's a kind of set of certain subcarrier. You are making a kind of one block, which will be when you schedule or allocate resources, we allocate RB by RB, not subcarrier by subcarrier. Okay. So that's a minimum unit which is allocated. I mean, multiple of that is allocated to a device. Okay.
So it means the device can have a maximum of 12 subcarriers at a time.
So multiple of RBs, not only one RB, but multiple of RB.
Sir,
Okay.
in case of 4G, the resource blocks are defined in terms of frequency as well as time division also.
Time. For
Yeah,
a certain,
like 15 kilohertz with 10 millisecond
yeah,
time.
you're right. So in case of 4G, resource block is 12 subcarrier in certain time. A time is also defined there, right?
Yes.
But
Yes.
in 5G, since that time is variable, that time I'll be discussing is very much variable. Sometime it is X, sometime it is X by 2, sometime it is X by 4. So here time is not defined. The source block is just a 12 continuous subcarrier.
So during initiation of the session, whether that time duration is negotiated between UE and the network?
Yes, there is a process of synchronization in 5G, similar to 4G, which I have a session on that, so you can go through. So there is a synchronization process. If time permit, I'll take that session also. So let us summarize this.
Thank you, sir.
One last question, sir.
Yeah,
Sir,
please.
you said that in the case of control signals, the higher numerology would be used. That corresponds to the higher capacity. But on contrary, the for control signals, we require lesser bandwidth. So they should be allocated lowest numerology. Why we allocate higher numerology for the control signals then?
So basically, it's not a question of which numerology you are using for control signaling. In 5G, both are independent. So for example, in a same frame, if data is using one numerology, your control can use some other numerology, right? So these two has been made very, very independent, right? For example, maybe it is possible that I am using 15 kilohertz for data and 30 kilohertz for signaling. That is a possibility in 5G. It's very, very configurable. That's why they have defined both separately. Secondly, for 240 kilohertz, till release 16, they have only defined use in the control signaling, not in the data. Perhaps going forward, they will also use it for data. So, I mean, the way system evolves and they're able to use it, they keep adding into the specifications. So that is not end of the road. That is just evolving, right? I think this summary I have already covered that in case of 15 kilohertz, the maximum channel bandwidth possible is 50 kilohertz, then 100 kilohertz in case of 30 and 60 kilohertz subcarrier spacing. In FR2, 60, I have 200 megahertz bandwidth. In case of 120, I have 400, and for 240 also, it can be up to 400 megahertz, but it is only used for signaling. Just look at this particular picture in a very broad sense. I have taken it from one of the document released by Qualcomm. What is use cases of different frequencies, spectrum band and cell size. So here they are talking about outdoor macro coverage. That means a large coverage. And they have taken example of 700 megahertz FDD band. So lower side of the frequency band will use lower numerology. So in this example, this is just an example. It is not fixed that 700 megahertz will use 15 kilohertz only. This is just an example to tell you. And what are the channel bandwidth can be used? 5, 10 or 20, because you will not have more channel bandwidth in these 700 megahertz or 900 megahertz bands. Now, other example they have given is of mid band, 3 to 5 gigahertz or 3.5 gigahertz. So we know that these bands are TDD. So here they have talked about using 30 kilohertz subcarrier spacing and channel bandwidth of 100 megahertz. Yesterday also we were talking that in mid band in India also we can at most give about 80-100 megahertz to our operators in 3.5 gigahertz band. So that is for outdoor macro and a small cell coverage. And for indoor wideband coverage, unlicensed band, may I request all of you to kindly mute yourself? Yeah, thank you. So here we are talking about 60 kilohertz subcarrier spacing and whatever channel bandwidth we may have. And then we have 28 gigahertz, that is millimeter wave. So here we'll be using 120 kilohertz and channel bandwidth can go up to 400 megahertz. So Sanjay question is getting answered that lower side of the band we are using lower numerology, higher side of band we are using higher numerology. Okay. Just look at this particular picture. It's very interesting diagram. I'll explain this. I have taken from one very good resource, that is empirical.com. Empirical.com, you can note it down. A lot of resource 5G related it is there. They have just compared the various numerology, cell size, latency, etc. So on this axis we have frequencies, right? So here it is sub 1 gigahertz. Then we have mid band and then we have say very high millimeter wave. So let us talk about sub 1 gigahertz, right? So the question is whether I can use 15 kilohertz or 30 kilohertz or 60 kilohertz or what. So we know that if I use 15 kilohertz into the lower side of the bandwidth, channel bandwidth, that is less than 1 gigahertz, I can have large coverage, large cell size. But since signal has to travel a larger distance and come back, my latency will be less. So here if you look at latency, my latency will be medium, right? But suppose I use same 15 kilohertz and have medium kind of coverage, small kind of coverage, it is possible. I can reduce the coverage by reducing the power. So I can have better latency here, slightly better latency here. But the disadvantage is that the 15 kilohertz numerology frame structure is designed in such a way that it can cater to this much coverage. That means the cyclic prefix, or you can say time guard band is defined in such a way that inter-symbol interference is avoided. But in case I'm using it for lower coverage or the medium cell size, actually I am wasting the resources in terms of time because I have provisioned a larger time, but I'm not utilizing because my coverage is less, right? So it is not wise to use lesser coverage with 15 kilohertz and lower side of the bandwidth. Again here, if you see with 15 kilohertz, I can even create a small cell and I can get in very, very low latency. But the problem is here, a lot of resources are getting wasted because of the high time guard band or CP size, which is highest among all numerology. Okay. Now suppose I use 30 kilohertz of carrier spacing here and I have a medium coverage, right? So I can always use, there is no problem, but I cannot have larger coverage because the CP size defined for 30 kilohertz is not for larger coverage. It will be inter-symbol interference in case I use 30 kilohertz for larger coverage. I can use it for small cell. Now let us take example of medium bands, say 2100 megahertz band. So there, if you look at 30 kilohertz, I can say create this much coverage, medium side of coverage. I'll have low latency. If I have smaller coverage, I can create very low latency and so on. So basically just you are able to see here relation between a cell size, numerology, latency and coverage. Any question here? Any
Yes,
question?
Ashokji, I was having one question. I was waiting for this because you are flowing, so I did not stop. My fundamental question is that with a 15 kilohertz of the this that band, the 15 kilohertz when you choose, then you can go up till 50 megahertz bandwidth only, that is permitted. With
Yes.
15 kilohertz cap, 50 megahertz. What is that? That could you explain that how that limiting factor is achieved? Like,
Okay, so
why
that
is it up to 50?
limiting factor is nothing but how much sampling rate you can achieve with today's whatever hardware and software you have, right? So, so if you see in terms of total number of RBs and all, so that is getting limited in different numerology, different. So maximum they are using 275 RBs, right? And accordingly you have number of subcarriers and all those sampling rates are decided. So it is all because of the limitation onto the hardware side. These limit have been put by the specification, sir.
Okay, thank you. Thank you.
Okay. Now let us look at concept of carrier aggregation. It's very simple that in case of 5G, the carrier aggregation is possible in all permutation and combination. So the first is the intra-band contiguous. In case, suppose you have a frequency band A and there are two carrier component. So those two carrier component can be used for carrier aggregation. In case you have intra-band same but non-contiguous, one carrier component is here and then you have some gap and then you have some other carrier component. So this kind of a carrier component can also be aggregated. Now you have interband. That means one is frequency band A, other is frequency band B, and the component carrier 1 is here, component carrier 2 is here. So this can also be carrier aggregated in case of 5G. This was also possible in 4G. So let us look at what kind of carrier aggregation LT was having. So when LT Advanced came, LT Advanced was which release of 3GPP? Can somebody tell me? Anyone from you? Which release of 3GPP was LT Advanced?
14, sir. Release 14.
No.
Release 16. Release 16.
No. So release 8 was the first
11.
release of LTE and release 10 was LTE Advanced. So in release 10, when LTE Advanced came, they came out with carrier aggregation in 4G. And there they said that 5 carrier can be aggregated. So yesterday we had discussed that in case of 4G, channel bandwidth is 20 megahertz. So the maximum channel bandwidth one can achieve using carrier aggregation is 20 into 5, that is 100 megahertz, right? Later in release 13, R13, they came out with the concept of 32 carrier component aggregation, but perhaps this was not used and people were still on release 10, etc. Okay. So let us understand concept of carrier aggregation. In this example, what I'm taking that I have two carrier which are contiguous and in the same band, that is intra band contiguous, and in addition I have one carrier in band 2. So in case a carrier aggregation has to be used, and let us also assume that these are lower side of the band and this is kind of higher side of the band, higher frequency band. So what happens is that this blue color C, this blue one is the outer coverage which one is getting with this frequency. So this becomes the lowest frequency becomes the primary serving cell or the primary component carrier. So on this your data and control signaling both is taken care of. Now on the second, this green one is your secondary serving cell, and here we use only user data. The control signaling is only going on this blue frequency band, and this band 2 also is a secondary serving cell and only used for data. So that means the control signaling is only on one frequency band, that is on lower side, so that signaling coverage is across the coverage, and rest of the carrier are being used for carrying only the user data. So that is the concept of carrier aggregation. I have given a link. You can read this particular article given on 3GPP website. In case of 5G, theoretically 16 carrier can be.
Sir,
Yeah, please go ahead.
sir, can you put that link in the chat box?
So I have given this PPT to you, PDF. You can copy and paste.
Yeah, we can do it, but right now, like, if you can do it, that will be better. Okay, no problem.
Okay, it's there in the PDF. You can always copy and paste, right? Okay, in case of 5G, 16 carrier component can be aggregated. That is a kind of a vision, but those will be achieved slowly. So as of now, they have achieved aggregation of few carriers, and up to 1.2 gigahertz channel bandwidth they are able to achieve up to release 16, right? Other concept is that every carrier component can have different numerology. You can use FTDD in one carrier, FDD in other carrier. You can use licensed band and also unlicensed band and do a carrier aggregation. And yesterday we had discussed supplementary uplink and downlink. So you can also carrier aggregate with SUL and SDL. So all permutation combinations are possible in 5G. So same here up to 16 carrier aggregation, and also you can use supplementary uplink or downlink. Now let us look at various use cases of carrier aggregation. So just yesterday somebody had asked me about SA and NSA mode. I had explained that the NSA mode is when you deploy 5G radio into the 4G network. We call it NSA, non-standalone. And SA means you have 5G core and 5G radio. So in this example, just see, just look, I mean, I have just, for understanding, I have taken the example that suppose this tower has 4G and 5G base station both in a NSA mode, and 4G is on say 2.1 gigahertz band, right? So 4G coverage shown here is the larger one, this one, the green color, and 5G is on say 3.5 gigahertz, slightly higher band. So the coverage will be less. Coverage will be like this. right? So that means in this area, 5G uplink and downlink both will be available. But as I was saying yesterday that for downlink purpose, even 5G can cover this much area. This area can be covered even by 5G. So it has got 5G downlink coverage. So when your device is here in the blue area, it can connect to 4G and 5G base station both, and that we call it dual connectivity. And you can have double the data, 4G data as well as 5G data, in uplink also and downlink also. But in case your device is in this green area, so the downlink side you can have 4G data and 5G. Downlink side you can have 4G data and 5G data. But for uplink, it will only be using the 4G base station. So this is a use case wherein you have 4G and 5G BTS both, and a device capable of 5G can use the dual connectivity concept, double the data and uplink downlink in blue area, and green area double the downlink but uplink only the 4G capacity. So this is one of the use case. Now let's look at the other use case. In this example, we are talking about both carrier of 5G but different frequency band. It's similar one. So say 2.1 gigahertz and 3.5 gigahertz, two carriers. So definitely 2.1 will have a larger coverage and 3.5 slightly smaller. Similar concept, when your device is here in the blue area, it is able to use carrier aggregation in both uplink and downlink. But if it is in greener area, in downlink side, it is able to carrier aggregate. Uplink side, it is only using the 2.1 gigahertz. So that is the use case. Next use case is about the supplementary uplink or downlink, right? So generally uplink to increase the coverage. So what you see here is that on the normal frequency which is base station is using, here you will have downlink and uplink both, but downlink will be extended slightly more. But with SUL you can have uplink coverage here with a slightly lower frequency. So this is kind of how you can increase the coverage. Yesterday I was talking about this concept. Okay, same picture in a different kind of diagram. It is similar one. This is supplementary uplink. Now there is a concept of carrier aggregation using the unlicensed band, right? So what we're talking about, that one carrier we have a licensed, which is allocated by licensor, say DOT in India. Another is the unlicensed band, the free band which anyone can use. This can also be aggregated. So now there are two concepts, NSA mode and SA mode. So let us take example of NSA mode where I have EPC, that is 4G core, evolved packet core. I have 4G BTS, that is called LTE. And then I have new radio, that is 5G. And U means operating in unlicensed band. So in this example, the anchor BTS is LTE and secondary BTS is your 5G BTS working on unlicensed. The device can connect to LTE as well as the new radio and can use the dual connectivity concept and double the data. Or if it is very near to NRU, it can connect to NRU and utilize the 5G data. So this is concept of carrier aggregation in unlicensed band. Okay, any question up till now? Shall I proceed? Just say yes, no in chat box.
I had one question.
Yes, sir.
When you discuss that control signals and data signals, and
Yes.
control signals can have wider reach. It can cover larger distance. If
Yeah.
you give it a lower frequency, it will travel larger distance and it will have
Yes.
that. So only doubt that arose in that point of time was, this control signal and data signal, because ultimately if the cell size is bigger, then latency increases. And what we are trying to do, we are putting the two things, like one data is less latency and the control is more latency. So how do we combine it? I mean, does it not cause any problem when we transmit it? That was my only doubt.
So you're right, sir. So even for the lower frequency band, which I'm talking about, it's not very low, and maybe whatever variation in the latency will be. So these are use cases, sir. In case a pure latency related applications is required, perhaps I'll be using the higher band, higher numerology for that. If latency becomes a very critical requirement. For example, you have EMBB application, you have MMTC application. For example, MMTC or EMBB may not require that much latency, but only URLLC applications will require a very high latency. So these are various. 5G is kind of one coverage or one kind of use case is not there. There is a varied use case, and for every use case there is a set of requirement or set of kind of configuration we can do, sir.
Okay, thank you so much. Good answer. Yes.
So now,
Sir, will you please,
yeah,
sir,
go
will you
ahead.
please explain the previous slide, sir, please, once again?
This
Previous
one,
slide. Yes, that one.
this one.
Yes, sir.
So okay. So here I am saying that 5G system is also designed so that you can aggregate licensed band, which you get from DOT in India, and also the unlicensed band. Our Wi-Fi works on an unlicensed band, right? So these two carrier can be aggregated in 5G. Now 5G has two mode of operation as of now. One is NSA mode, non-standalone, another is SA mode. In case of NSA, the 5G BTS gets connected to 4G core, that is EPC. So you have 4G BTS as well as 5G BTS. So basically the 4G is the master BTS and 5G is the slave BTS kind of. But the device, a 5G device can connect to both, dual connectivity, and have a good data, better data compared to only LTE. In case of a standalone, the normal new radio and the unlicensed band radio, both one will be on one licensed band, other will be on licensed band, and your device can have dual connectivity with this and this also, both devices, or depending upon what coverage it is getting, so it will get a higher data. So that is a kind of a carrier aggregation. Is it clear now?
Yes, sir. Thank you, sir.
Okay, the next part is bandwidth part. Let me explain you what is bandwidth part. First of all, let me explain you in case of 4G, that's an issue with 4G, that our devices, mobile phone has to be designed for the entire channel bandwidth of 20 megahertz. Your 4G phones are always designed for the full channel bandwidth of 20 megahertz. And that's why we see that our battery get discharged very fast, right? But in case of 5G, since we support up to 400 megahertz, it was not wise to make mandatory for a device to operate on the full channel bandwidth. So the concept of bandwidth part came, that you can divide the channel bandwidth into chunk of bandwidth part, right? And your device can use any of them, either the smaller bandwidth part or the bigger bandwidth part as per the requirement. So that is the concept of. So what is a bandwidth part? It is a contiguous resource block within the channel bandwidth, and each channel bandwidth can have its own numerology, either same numerology in all the bandwidth part, or it can have a different one. And a UV can be configured for 4 BWP in downlink and 4 in uplink. In case you have supplementary link, you can use another 4 BWP. Yeah, any question? Any question here?
Yes, sir. So there is already a concept of resource block where you can allocate one or more than one resource block to any UE. then why there is a requirement of then another concept of bandwidth part for the same purpose?
Very right. So what happens when you switch on your mobile? Actually, it search into the entire channel bandwidth in case of 4G, right? So you have to search from beginning to end to latch to the network, right? But in case of bandwidth part, every bandwidth part will have its own control signaling. So you have to search within that only. So that I'll be explaining in the upcoming slide. Just hold on for a minute. It will be clear to you. So this example is that suppose you have this much channel bandwidth, but at a particular point of time, you are just say browsing the internet. Why to use the entire channel bandwidth at that particular time? So I use a smaller bandwidth part out of the whole. These DWP are already decided between the device and the network. That is one use case, that reduced UV bandwidth capability. Secondly is the reduced UV energy, that there are two BWP here shown. BWP2 is kind of a subset of BWP1, that whenever there is a less data required or energy consumption is required to be reduced, so it will use the lesser bandwidth part, otherwise it can use the bigger one. So this is possible. The other use case is that I have two bandwidth part. In one bandwidth part I am using one numerology, and other bandwidth part I am using other numerology. This is the three kind of a use cases. Fourth use cases is that suppose you have non-contiguous spectrum within the overall channel bandwidth. So I can define BWP1 here, BWP2 here, and this I'm not using today, maybe in future I'll use it, right? Similarly, I can leave some channel bandwidth for future services, right? So that is also a concept. Now, how bandwidth parts are used? Just see this picture, very famous picture. If you Google, you'll get this picture everywhere. So this is in frequency domain. These are RB or subcarrier, and this is time. So one device is using lesser bandwidth part, say BWP1, where this much frequency resources are being used, as say device is using just a browsing. Suddenly at this point of time, suppose it has started streaming some streaming service, so data required would be more, so it can use the larger BWP. It becomes active for some time till that streaming is happening, and again if streaming has stopped, so it will come back to BWP1, right? Smaller. So now let me answer Sanjay question further and ask a question from you guys also, that in case of a IoT, I was talking about IoT has to be very energy efficient, right? So if I design this IoT for 400 megahertz channel bandwidth, the complexity of IoT will be very high. Cost will also be very high, and the form factor will also be high. So how I can reduce the form factor? Since there is a concept of BWP, I can design a IoT device with only for say BWP1, very small bandwidth, and I know that a lower frequency band and very small bandwidth would be sufficient for IoT. So my IoT device will be very simple, cost effective, and my battery life can be very high because of this particular, because I need not use the entire channel bandwidth. So Sanjay, this is one of the reasons to have bandwidth part, in comparison to 4G, where even in IoT or wherever you have 4G devices, it has to support the entire 20 megahertz. Any question? Any question here?
Yes, sir. My question is that, sir, this BWP, who will be deciding? Network engineers, we will be deciding the what BWP has to be allocated, or it is as per the content from where we are taking streaming.
Yeah. Okay. Very right. Very good question. So in different bands, these bandwidth configurations are already defined in the standard. Why these are defined? So that while manufacturing, you know what you have to manufacture, right? It cannot be a dynamic. So technically you can do a dynamic configuration into the network, but they have given it into the standard itself so that when you're designing a device, you do not know what kind of network it is. So everybody will kind of configure the same BWP onto the network in different bands, and it can be utilized. Got my point?
Yes, sir.
Sir, how about the numerology and all? These are not hard.
Yeah, go ahead.
Numerology, this is being defined by the user.
Not user do not define anything. It is the base station decides, and the use cases decide what kind of BWP will be using. So your device is very, very intelligent. It talks to the base station and uses a particular BWP for a particular service. There is a interaction between the device and the base station. Is that fine?
Yes, sir. By user, I meant the radio only, not the
Yeah.
movie. Radio
Yes.
only, I meant. Yeah.
UV has got a role. Now just see this particular picture. The core set is nothing but control resource set, control signaling. If you see the LT, your control signaling is spread across the subframe, right? 1 millisecond subframe. Everywhere this control signaling will be there. And that's why a LT device has to support the entire channel bandwidth so that it can latch to the network or use the control signals. In case of 5G, every BWP will have its own set of control resources. That's why we call it self-contained slots in 5G. That means tomorrow if technology change, I can use different technology here. I can use different technology here because they are separated in time domain and not dependent upon the other BWP. That's a very, very beautiful concept in new radio, which makes it very, very flexible in terms of numerology. So here I can use different numerology. Here I can use different numerology. Today I am using OFDMA. Tomorrow I can use NOMA here and continue OFDM here. That's why we call it future compatible technology. The 5G is also said future compatible. So the way they have designed that it is kind of a future compatible and new innovation can be accommodated and switchover is possible very smoothly. This part is over. You take 2-3 minutes break and then I'll be starting the next session, which is on 5G new radio frame structure.